So let's say that we have our synthesis of ammonia and the decomposition of ammonia in equilibrium. The rate of the forward reaction and the rate of the reverse reaction are the same. So we have some amount of nitrogen gas, some amount of hydrogen gas, and some amount of ammonia present. And these concentrations don't have to be the exact same number, but you'll have the concentration that's the same over time because we have the same rates going on throughout this equilibrium. Now let's say I increase the amount of hydrogen. I put more hydrogen gas into this system. So I have a lot more hydrogen. What is going to happen? Well, if I have more hydrogen around, there are more chances that hydrogen and nitrogen will react with each other in the correct orientation and with the correct amount of energy to form more ammonia. So you have an increase in the rate of the forward reaction. We have more of this reaction happening over time, and so the equilibrium has to shift. It has to go this way, eat up those hydrogens that we've introduced, and then you're going to make more of your ammonia. More ammonia will go back, and you'll find a new equilibrium. The same thing would happen if you increase the amount of nitrogen gas in the system. If we put more of a reactant in there, our rate of the forward reaction is going to increase in order to reestablish that equilibrium. So whenever you're putting a stress on the system tries to undo that stress, go back to a sense of equilibrium. So it makes sense if I put more ammonia in our reaction chamber, that's at equilibrium. If I increase the amount of this, we'll increase the rate of the reverse reaction. This sort of simple idea is what Le Chatelier's principle is all about. The very French Le Chatelier came up with this principle. When a system at equilibrium is subject to change in concentration, temperature, volume, or pressure, the system changes to a new equilibrium. The system will adjust or shift to counteract that change. Let's look at a general reaction. Here we have A plus B gives us C plus D. And there's a dynamic equilibrium going on, so there is a rate of our forward reaction and our rate of our reverse reaction is the same. And importantly, we have a delta H. We have an enthalpy of this reaction, and it's endothermic. It needs heat in order to go. That's what this plus 100 kilojoules is telling us. Enthalpies of reactions, so delta H's with a reaction, are written for the forward reaction. So A plus B needs 100 kilojoules of heat in order to make your products. To figure out how a change in temperature is going to shift your equilibrium, a tip is to rewrite the equation and put heat as a reactant or a product, depending on if it's exothermic or endothermic. So if we have an endothermic reaction like this and heat is needed, we can put heat as a reactant. And if heat is released, if your delta H, if your enthalpy of the reaction is negative, it's releasing heat, you could think of it as a product. It comes with the other products. Heat is released. To rewrite this general reaction with heat, we would put it as a reactant. What we're going to do is go through a series of stresses on the system, and we're going to predict which way the equilibrium will shift. And then we'll talk about why that shift happens. First, we're going to increase the amount of reactant A. We're going to increase that concentration of A, put more A into our system. Which way will equilibrium shift? Well, it's going to go away from A. So equilibrium is going to go towards the right, towards making more C and D. If the concentration of a reactant is increased, more forward reaction is going to happen to produce more of our product. What happens if we increase the amount of reactant B? Well, reactant B is just like reactant A. It's one of our reactants. So that means our equilibrium is going to again shift to the right. And it's going to be for the exact same reason. You have more B, you have more A, you have more reactant. Well, you're going to have more chances for that forward reaction to happen. If we increase the amount of product C, well, now it's more likely that the reaction in the reverse will take place. that you'll make your reactants. So the reverse reaction is going to take place more often. We've shifted equilibrium to the left. An increase in the amount of product D will give you the same result as an increase in product C. Any increase on this side means that equilibrium is going to shift to the left to eat up all of that extra product. If the temperature is increased, for this specific reaction that we have here, heat is a reactant. So if we increase the temperature, we're increasing the amount of heat. That's just like if we were increasing a reactant. So equilibrium is going to shift to the right. If we decrease the temperature, so if we're removing heat, well, now the reaction will shift to the left, towards the heat. More heat is needed, and the endothermic reaction is not favored, so we'll have the reverse reaction happen. An increase in pressure. Well, if your reactants and products are all solids or liquids, this wouldn't matter, but it does matter when you're dealing with gases. So gases do not like to be all scrunched up next to each other. So whatever side has more gases, that's the side that's going to be less favored. We're increasing the pressure, the volume is decreasing. We know that from our gas laws. So the concentration of your gases are increasing. If one side has more concentration, it increases. So for this, we're going to shift to the left, towards the smaller number of gas particles. Decrease in gas pressure. Well, this is just like the reverse. Now we're going to shift to the right. We're going to shift towards the larger number of gas particles. As our pressure decreases, volume increases, concentration of moles of gas decreases, and if one side has more concentration, decreases, it will shift towards that side. So less pressure, more moles of gas is favored, we're going to shift to the right. So what happens when you add a catalyst? Well, a catalyst normally speeds up a chemical reaction, but what it actually does is it increases the rate of both the forward and the reverse reactions. So it doesn't favor one side or the other. A catalyst is an extra substance that you add to a chemical reaction that increases the rate of a chemical reaction without undergoing any permanent change. So platinum catalysts, even though they're very expensive, are used because you can recover all of your platinum at the end of the reaction. One last question. Which direction will this reaction shift if the temperature is increased? So this is the same reaction we've been looking at. Here, delta H, the change in enthalpy, is negative. What that means is heat is released. If heat is released, we can think of it as it being produced for the forward reaction. So you can rewrite it as a product. You can also just write plus heat. I do that. Now, if we're increasing the temperature, we're adding more heat, which way is equilibrium going to shift? Well, it's going to shift to the left, away from the heat. So your endothermic reverse reaction is going to be favored.